All right, let's talk about something that's happening all around you, right this second, but you probably never even think about it. It's a hidden law of physics. It's why you feel the warmth from a campfire and why your hot coffee eventually gets cold. Today, we're going to pull back the curtain on the secret science of heat and talk about something called Fourier's law. So, to kick things off, I've got a puzzle for you. It's about a super common experience, something you've probably felt before, and it seems like it just shouldn't make any sense. But trust me, the answer to this little puzzle, it's the key to understanding this whole thing. I mean, really think about that for a second. You could go out there with a thermometer, right, and prove scientifically that they are the exact same temperature. But your hand, your body, tells you something totally different. The metal feels freezing and the wood, well, it just feels kind of cool. This isn't some kind of magic trick. This is physics getting personal. And the reason why is actually pretty amazing. So, to crack this puzzle, we've got to take a little trip back in time. We're headed to the early 1800s to meet a brilliant French mathematician named Joseph Fourier. This guy came up with a really simple but totally game-changing idea about how heat gets from one place to another.
Okay, so the basic idea? It's super intuitive. I mean, we all know this. Heat flows from hot things to cold things. Duh, right? But here's where Fourier was a genius. He didn't just say that it flows, he asked, how fast does it flow? And he figured out that it really boils down to two big things: what the object is made of, and just how big that temperature difference is. To really get a handle on this, let's break it down into three simple parts.
First, we've got something called heat flux. Sounds complicated, but it's not. It's really just a term for the speed of heat. Think of it like a river. Heat flux is like asking, how much water is flowing past this rock every single second? It's not the total amount of heat we care about here, it's all about how fast that heat is moving.
All right, next up is the temperature gradient. This is the why. It's what makes the heat move in the first place. And the hill analogy is perfect here. You know how water flows way faster down a super steep hill than a gentle slope? It's the same exact idea with heat. A huge temperature difference over a tiny distance, that's a really steep heat hill. And it makes that heat just rush from the hot side to the cold side.
And that brings us to the final piece of our puzzle, thermal conductivity. Now this one is all about the stuff an object is made of. It's basically a measure of how good that material is at letting heat travel through it. Think of it as a heat highway. And this, right here, is the key to our whole bench mystery. Metal, that's like a massive 8-lane superhighway for heat. And wood, well, that's more like a little bumpy country road.
Okay, so let's recap. We've got the speed of the heat, we've got the steepness of the heat hill, and we have the width of the heat highway. We've got all the pieces. Now let's look at how scientists and physicists take these simple ideas and wrap them up into one super elegant package, the language of math.
Whoa, okay. I know. You see an equation like that and your brain might just want to check out. But hang on, don't panic. I promise you already get what this is saying. This is just the fancy shorthand way of writing down everything we just talked about. Let's break it down. See, it's all right there. That Q, that's our heat flux, the speed of the heat flow. The K, that's thermal conductivity, how wide our heat highway is. And that triangle T thing, grad T, that's just our temperature gradient, how steep the hill is. Oh, and the minus sign, that's just a little reminder that heat is always flowing down the hill, from hot to cold. So all this equation is really saying is, the speed of the heat depends on how wide the highway is and how steep the hill is. That's literally it.
Now that equation is unbelievably powerful. It tells you exactly what's happening with heat at any single tiny point in the universe. But what if you're an engineer trying to build something? You're not just looking at one point, you're looking at a whole thing, right? You need to know how heat moves through an entire object. So how do we take this universal law and make it, practical?
Yeah, that beautiful fundamental equation is perfect for a physicist, but how does it help us figure out the heat flowing through a real object, something with a specific thickness and a specific size, like, say, an entire wall of your house or a pane of glass in a window?
Well, for that, engineers have a much more hands-on tool. It's a simplified version called conductance. What it does is it takes Fourier's big idea, that fundamental law, and it sort of bakes in the real-world details of an object. Its actual thickness, its area, the whole deal. It basically answers the simple question, okay, for this specific window, how much heat is actually getting through?
So you can see there are really just two different ways of looking at the same thing. The fancy differential form, that's the pure fundamental law that physicists use to understand how the universe ticks. And the conductance version? That's the practical, roll-up-your-sleeves tool that engineers use to actually build things in that universe, or at least build things that don't melt or freeze.
Okay, so why does any of this matter? This law is from the 1800s, right? Who cares? Well, we all should. Because learning how to control the flow of heat is one of the most important things in our modern world. And once you start looking for it, you see its fingerprints absolutely everywhere, sometimes in the most unexpected places. Think about it. That cozy feeling in your house during a blizzard? That's thanks to insulation that was designed using Fourier's law. The fact that your smartphone, which is basically a tiny supercomputer, doesn't just melt in your pocket, that's because of heat sinks, little metal fins designed to pull heat away as fast as possible. We're talking about everything from the heat shields that keep astronauts safe coming back to Earth to getting that perfect crispy pizza crust and even understanding how a penguin's feathers keep it alive in Antarctica. It all comes back to this one simple idea.
And that brings us full circle right back to our park bench. The mystery's solved. The metal bench doesn't feel colder because it is colder. It feels colder because it's a heat-stealing machine. It's a superhighway. It has a super high thermal conductivity, a big K value, and it just yanks the heat out of your body at an incredible rate. The wood, on the other hand, with its low K value, it's that slow, lazy country road. The heat leaves your body much, much slower, and so it just doesn't feel as cold.
So there you have it. A really simple idea that explains everything from why a park bench feels cold to how a spaceship survives. It literally shapes the world we live in. And now, you get it. You understand the secret language of how heat moves. So the only real question left is, now that you know the rules, what are you going to build?